Good morning everyone, I am Daika Stella May Del Rio from BSSE-2103 and today I'll be presenting our study on predicting the impact of engineering waste rocks on water quality during the construction of the Dahe Reservoir. This study was conducted by Yagao, Hang Tao, Fei Fang Li, and Bang Junhan. This project addresses both the opportunities and challenges of reservoir construction, especially regarding ecological and water quality concerns. So here we will be discussing the importance of reservoir construction for water and energy needs, the challenges, ecological and water quality, risks during constructions, and the impacts during the construction phase. Impounding water through dams and construction reservoir is one of the fundamental ways to address water supply issues and advance low-carbon energy on a global scale. However, reservoir construction has both advantages and disadvantages, and it has been criticized for the risk it poses to the ecological environment. The safety risk and ecological impacts of dams and reservoir have been receiving increasing attention, predicting ecological and environmental problems that may arise during the planning and construction period, and identifying the sources of risk to water security that they may cause have gradually become important scientific concerns. Currently, research on the ecological and environmental impacts of reservoir construction primarily focuses on two aspects: the migration and release of residual pollutants from soil and waste in the reservoir are caused by the process of water storage, leading to impacts on water quality and ecological changes. Second, the construction of reservoir has significantly changed the natural flow and hydrological pattern of the river, impacting river aquatic life, fish, and basins habitats. This has also led to changes in river sediments yield due to reservoir construction or sedimentation in the reservoir, resulting in significant environmental impacts. However, these studies primarily focused on water quality and ecological environmental issues following reservoir storage and operations. Studies have highlighted the environmental risks associated with reservoir construction, such as land occupation, earth and stone excavation, rock and slag generation, sewage discharge, dust, flying dust, and on-site construction noise. Several studies have utilized mathematical models and other methods to analyze and clarify the primarily environmental risks associated with the reservoir construction process. However, there is still a lack of systematic research and quantitative evaluation of such risks and their sources in the reservoir construction process. So next, the study objective. Predict water quality impacts caused by the sulfur and iron-rich engineering waste rocks during the construction of the Dahe Reservoir. This study focuses on Dahe Reservoir, a newly constructed reservoir in southwest China. This study aims to predict and analyze the potential impact of engineering waste containing sulfur and iron at the bottom of the reservoir on water quality by developing a three-dimensional water quality model. The findings will offer valuable insights for conducting risk analysis during the construction of similar projects. On research area and methods in the study area, Dahe Reservoir is situated in Kiangsu Province. There are two waste rock yards located on the right and left banks of the river upstream at distance of 1.5 kilometers and 2 kilometers from the dam, respectively. According to on-site expert identification, thin section examination, and material characterization, it has been determined that the waste rocks mainly consist of mudstone and quartzite. Mudstone accounts for 5% to 10% and may contain pyrite or pyrrhotite. Acidic wastewater (ARD) will be generated in a prolonged oxidized environment, which potentially impact the quality of reservoir wastewater. The cross-section C1, C2, and C3 and C4 were set as shown in the figure 1 in the following study. So the next one is the hydrodynamic model. Based on the two-dimensional hydrodynamic model, a three-dimensional hydrodynamic model of Taher Reservoir was developed using the Mike 3 FMHD module. Incorporating vertical layering, the control equations include the Navier-Stokes equation with the business approximation and the assumption of the static pressure. The finite volume method based on the grid center is used to especially discretize the governing equations. In the three-dimensional model, the grid units consist of triangular prism or quadrilateral bricks in the horizontal plane. The sigma method was used to divide it into 3 layers at equal intervals, and the vertical thickness of each layer varies according to the water depth. According to the grid size and water depth conditions, the calculation of the time step is dynamically adjusted to ensure that the CFL number remains below 1. To meet the stability requirements of the model, the calculation time step size is adjusted within the range of 0.1 to 30 seconds. The Smagorinsky formula is employed to calculate the plane eddy viscosity coefficient with the Smagorinsky coefficient set as at 0.28. Additionally, the turbulence water model is utilized to calculate the real-time vertically eddy viscosity coefficient. The dry and wet which process in the specified area are calculated using the grid-based freezing method. Consider that the water is located in a mountainous canyon. The roughness of the height was selected as 0.1 meter by comparing it with the roughness value of the surrounding riverbed. The design data for the water level of the Daher Reservoir was used to compare with the corresponding calculated results of the model. The calculation period spanned from November 1 to May 2022, and the water level change in the reservoir is illustrated in Figure 2. The predicted water level in front of the dam closely matches the trend of the measured value and the hydrodynamic model that can accurately depict the dynamic process of water storage in the reservoir. So, the water quality model. The Ecolab module was utilized to construct the three-dimensional water quality models of Daher Reservoir, considering the characteristic indicators of acid rock drainage, pH, iron, and sulfur were selected as the parameters for the water quality model. The initial values were set as the follow: pH 7.47, iron 0.01, and sulfur 23.60 mg per liters. Based on the water quality monitoring data from the dry seasons in the upper reaches. In the model settings, the quantity of each pollutant release was determined based on the water level when the stockyard was flooded, in the conjunction with the research. To analyze water quality risk more effectively, it is assumed based on the precautionary principle that the release of pollutants begins when the waste rocks are submerged. The maximum daily released amount was utilized to calculate the maximum released amount of each indicator at different water levels. That shows on the table number 1, and the model was introduced for calculation. So, moving to the results and discussion, the concentration distribution of the pollutants. Based on the calculation results of the three-dimensional water quality model shows in Figure 3, it shows the distribution of the sulfur in milligram per liter, iron in milligram per liter, and pH in the surface, middle, and bottom layers of Daher Reservoir at typical water levels after 60 days, 90 days, and 120 days of impoundment respectively. In general, the pH value of each layer in the reservoir did not drop below 6.5 during the water storage process. After 2 months of water storage, the release of pollutants from the waste rock yard significantly impacted the lower water, indicating a trend of spreading from the reservoir bottom of the upper layer, and it had a slight impact on the reservoir quality in the middle middle layer but had no noticeable effect on the surface water quality. On the 90th day, when the water level of the reservoir reaches 867 meters, pollutants continued to diffuse toward the water intake, significantly affecting the quality of the surface water. The highest concentration of sulfur and the iron and surface water are found in the above stockyard. The concentrations in the upper middle and the lower sections of CI are 24.43 mg per liter, 26.57 mg per liter, and 34.11 mg per liter, respectively. The concentrations in the upper middle and lower layers of C1 are 0.03 mg per liter, 0.03 mg per liter, and 16 mg per liter, which does not exceed the Class 3 water standards specified in Surface Water Environmental Quality Standards. When the reservoir was impounded for 120 days, the release of pollutants from the waste rock yards are essentially ceased. The pollutants released in the early stages gradually accumulated in front of the dam dilution and diffusion. At this time, the highest concentration of sulfur and iron in the water still occurred at the bottom near the dam. The concentration of sulfur in the upper, middle, and lower layers of the C4 sections were 26.63 mg per liter, 28.84 mg per liter, and 31.63 mg per liter, respectively. So next, the impact on water quality in front of the dam. The distribution of sulfur, iron, and pH in the C2 section 100 meters downstream of the stockyard were analyzed after 60 and 90 days of water storage. The trend of pollutants diffusion from the waste rock yards generally indicates vertical dispersion towards the surface water, gradually spreading towards the mid-water line. However, the fluctuation in the pollutants during the actual water storage process cannot be ignored. Tang et al. Reported that the directly regulating reservoir water's level may have a minimal impact on nutrient release in sediments, while water level changes can alter pH and the redox potential of the overlaying water, thereby indirectly affecting the release dynamics of nutrients in the sediments. Furthermore, it is important note that this study primarily focuses on the characteristic indicators of acid rock drainage or ARD released from the engineering waste such as pH value in the sulfate ions. The presence of heavy metals in the watershed still poses risk. Sarmiento et al. Demonstrated that the natural water bodies affected by ARD may accumulate significant amounts of heavy metals pollutants in their sediments. So for the conclusion and recommendation. In conclusion, the short-term water quality impacts during the construction, the long-term sediments monitoring importance. The hydrodynamic and water quality simulations in the study revealed that during the water storage process, pollutants released from the waste rock yards would impact the bottom water after 2 months. These pollutants would have been spread from the bottom of the reservoir to the upper layer with minimal impact of the surface water quality. After 3 months of water storage, when the water level reached 867 meters, the pollutants released by the waste rock had an impact of the surface water quality. After 4 months, the release of pollutants from the waste rock yards essentially ceased. However, the pollutants gradually accumulated in the bottom water body in front of the dam to dilution and diffusion. At this time, the concentrations of various indicators at the surface and middle water bodies were close to normal levels. Based on the engineering practices and of acid rocks drainage and combined with the model calculation results, this study concluded that the risk of ARD produced by the waste rock on reservoir water quality is minimal. However, the attention should be given to the long-term impact of the water quality of reservoir water. So that's all. Thank you.